Excellent, thanks. Hello everyone. Thanks Marietta for the introduction. So my name's Chris Mills. Thanks Marietta for introducing me as Dr. Chris Mills. That's always nice to hear. I recently just graduated or was awarded my engineering doctorate from Coventry University. I think it's the first time I've ever been referred to as a doctor, so quite nice. Family like to remind me that I'm not a real doctor, it's just a doctor of engineering I've got, but still it's nice all the same. So, hello everyone, welcome to today's webinar. As Marietta says, currently working from home, so hopefully the internet holds up. I'm sure it will. Hopefully you can all hear me and you enjoy today's presentation. So, in terms of a bit of background about myself, for those that don't know me, I've been at NEL now for over 12 years, since I graduated from Strathclyde University. I've got my background as chemical and process engineering, so I've got an honours degree in chemical process engineering. But I've worked for NEL now for 12 years, predominantly in flow measurement for liquids. I've also been involved in gas and multi-phase as well. Worked on a variety of R&D projects, consultancy projects, designing and building new facilities. So it's been very interesting over the last 12 years. One of the meters that I'm most familiar with, we calibrate a lot of here at NEL, is the Coriolis meter. So we've got a lot of data, a lot of research being completed with Coriolis meters, and I'm just going to present some of that to you today. So the title of this webinar is The Importance of Calibrating at Service Conditions. So on to the content slide. Hopefully you can see that. Hopefully it's moved on for you all. So the contents of today's presentation, bit of background. Then I'll talk about the Tuvsud National Engineering Laboratory facilities, a bit about the experience that we've gathered using these facilities, what we'd recommend, so how we'd recommend that end users calibrate and operate their flow meters, and then some conclusions. So you can see I've also included an image on this slide here. So that's just a commercially available Coriolis meter. That's a 3-inch device, and it's installed in one of our new facilities, or newer facilities at NEL, which is known as the Elevated Pressure and Temperature Facility. So that's located within the James Young building at NEL, which again is located in Glasgow, or East Kilbride, just outside of Glasgow in Scotland. So that's a typical arrangement for installing a Coriolis flow meter in one of our facilities. So I'm going to give you a brief history, background in terms of some of the research we've completed that forms part of this presentation / webinar today. So I joined NEL back, as I said, 12 years ago now, which is 2008. One of the first projects I was involved in was looking at high viscosity fluids and the effects on conventional flow meters. So it wasn't just Coriolis meters, we looked at Coriolis, ultrasonic, turbine meters, positive displacement, and Venturi and orifice meters as well. So we kind of looked at a vast array of conventional liquid flow meters to see how they performed with medium to high viscosity fluids. So this ranged from typically 50 to 2000 centipoise, so fairly viscous. We operated right across the laminar turbulent transitional flow regime. We then followed that up by, in 2010, we started looking at the effects of elevated temperatures on flow meters. Apologies if you hear me pause at any point, it's not that the sound's disappeared, it might be just be that I'm taking a drink of my coffee. But back in 2010, we were approached by an oil and gas operator in the North Sea who was swapping out their turbine meters for Coriolis devices. And they were going to be operating, or they were operating at elevated temperatures, typically in the region of about 70 degrees Celsius. Now, historically, calibration laboratories such as NEL and those located all around the world normally operate close to ambient, around about between 15 to 25 degrees Celsius, although many, including NEL, can operate at higher, up to about 40, 50 degrees Celsius. It was always thought that temperature didn't have a big effect on flow meters, and that's historically due to the flow meters being positive displacement, turbine, differential pressure devices. But this end user wanted to know if there was an effect of elevated temperature on Coriolis flow meters. So we managed to get a couple of Coriolis flow meters from the main manufacturers, a variety of sizes, and completed some preliminary investigations at NEL using our oil flow facility. From a couple of adaptations, we managed to operate up to close to 70 degrees Celsius, very stable temperature control, and we noted that there appeared to be a slight temperature dependence, not extremely large, but certainly more so than most people were aware of at the time. Bear in mind, this was 10 years ago now. So from that, we followed up with a JIP. So that's a joint industry project. So I ended up formulating a larger project looking at a variety of effects. So I already knew about viscosity / velocity profile, Reynolds number effects on Coriolis meters from the previous high viscosity research. We then had the elevated temperature research and also considered what about pressure. From looking at the manufacturer's specifications, some of them mentioned pressure effects, others didn't, but the values weren't traceable as well. You can find out where the research was from that they derived these corrections. So we formulated a GIP. We managed to get several sponsors for this large project, which was great. So I think we had in the end between I think it was about 10 or a dozen sponsors, which was fantastic. Looking at the main Coriolis manufacturers, so we had the three main manufacturers, and that was Hauser, Emerson Micromotion, and Krone. And we tested a variety of their commercially available Coriolis meters in a couple of different sizes, 3-inch and 4-inch in particular. And one of the main outputs from that project, so it finished in 2014, one of the main outputs was that there was a requirement for a new facility, a facility that could calibrate Coriolis flow meters close to service conditions, be it temperature and pressure. We already had the high viscosity facility. So we built this new facility from 2014 to 2016. It was operational. And then in that time, so that's almost 5 years now, it was ready around about 2015, 2016. So 4 or 5 years' time, we've completed a lot of research with that facility and also standard commercial calibrations. It's an extremely popular and extremely busy facility. So we have a lot of data available. So that's basically taking us up to the present day just now. So I've got a lot of data, both high viscosity and also from this new facility. And that was the one that I showed you the image of at the start, the elevated pressure and temperature flow facility, which is a liquid-based facility. So that's a brief bit of background on how we got to this point and where the data comes from this presentation. I'm also going to talk to you a bit about regulations and standards, everyone's favourite topics, not at all boring. Regulations, so in the UK, we have the UK Oil and Gas Authority, OGA, who publishes our guidelines. They mention a few things about Coriolis meters, but they also discuss temperature and pressure compensation as well. So I'm not going to read that out to you, but ultimately what I want to highlight here is they do mention that there is an effect of temperature and pressure, and if you're going to be operating at elevated conditions, your corrections that you're going to be applying, if required, have to be traceable. So that ultimately means that you have to go to a facility such as NEL's, and others are available, maybe not with such a wide operating range, but there are plenty of other flow facilities. You have to derive a correction from a traceable facility such as NEL's. Also, the same is true for viscosity. You can see that very last line there. The use of generic pressure, temperature, and/or viscosity correction factors must be agreed with OGA. So you're really wanting to try and derive traceable correction factors and have them fully traceable and auditable by OGA if required. So the regulations do mention that there is an effect. What about the ISO standard? So that's the 10790. That was last revised in 2015. It's up for revision this year. It's still to be voted upon in ballot whether it's to be revised or not. Personally, I hope that it is, because I think there's a lot of data NEL have gathered and would like to share that with the standard to hopefully inform industry. But this is, again, some snippets from the ISO standard. Again, I'm not going to read it all out verbatim. I'm just going to put it up on the screen. You can scan through it if you wish. Ultimately, the standard tells you that there is temperature compensation in a Coriolis meter. It tells you that there could be a pressure effect, and also that there could be a viscosity effect as well. It doesn't tell you too much more. Crucially, it doesn't really tell you how to compensate for these effects. I like to think that the standard should maybe provide more guidance to the end user. So recommend that you calibrate at conditions if possible and use a traceable correction if required. At present, I don't think it's overly helpful, the Coriolis ISO standard, hence why I'd like to see it revised with real data for temperature, pressure, and viscosity / Reynolds number effects. Then we have the other main standard that people be aware of, which is API MPMS 5.6, so American Petroleum Institute 5.6, and that was last revised in 2013. It was actually revised again in 2018 and then went to ballot but got rejected. So I think they might be looking at it again this year, but after the last one getting rejected, I think they might be waiting 5 years before it gets revised again. So I'm not 100% sure on that, the status of that one, although I have been contacted by API to potentially help write a future revision. It's just I don't think it's at the top of their agenda at present. So in terms of viscosity, they actually state there's no data to show changes in fluid viscosity affect the accuracy, which is obviously incorrect, although remember this is back in 2013. There is a lot of data now. NAL have written several papers. I've got journal papers, conference papers, even before 2013, but I can understand maybe they weren't fully aware of it back in 2012, 2013 when this was published. But there is viscosity effect, so I'd like to revise that. They mentioned a bit about pressure. So that is captured in the standard, but again, they're not really telling you exactly what to do about it, how to remedy it. And again, same is true of temperature. So for me, I think the standards could definitely do with being revised, providing more guidance to end users. So that's why I've got this nice badge here, basically just saying I don't think they're, I say not helpful, maybe not overly helpful. They're helpful in various parts, but I think they could do more for regards to operating at service conditions. So this is the new flow facility, or the newer flow facility that I mentioned earlier, the elevated pressure and temperature facility known as EPAT. So you can see here we have a closed loop system. So I was involved in the design and build of this facility, achieving accreditation and the operation of it for the last few years. So it's a closed loop system. We have two main pumps. We've got an inline heat exchanger, you can see in the top left. I'm not sure if my mouse tracks here, if you can see it or not. That's the heat exchanger. It flows around through here. There's a bypass system, takes it through a compact prover. So that's the Emerson Daniels 60 litre compact prover. We have the S600 plus flow computer that works alongside that for pulse interpolation of our turbine meters. As you can see that the outlet goes through various manifolds. So we've got 3 banks of turbine meters. So these are Fuhrer-Hermann helical blade turbines, ranging from 1.5 inch, 3 inch, and 6 inch in diameter. Flows back round into the test section. We've got 2 main test sections. We have a 6 inch line, the main line, and then we have a bypass 3 inch line. We have double block and bleed valves so that we can direct through either or, and then it flows back round again. This here is our pressurization unit, so that controls the pressure in the line. It keeps it stable within plus or minus 0.25 bar. In terms of operational conditions, this flow facility operates from 4 to 100 bar gauge, from 20 degrees Celsius to 80 degrees Celsius, and nominally from 0.5 to 100 litres a second. It operates with a mineral oil, approximate density in the region of 830 kilogram per meter cubed, and relatively low to medium viscosity of between 2 and 6 centipoise, depending on, of course, the temperature of the facility. Temperature can be kept stable within plus or minus 0.25 degrees C, and that's for the entire calibration. For a specific test point, the temperature and pressure is normally more stable than that. In terms of uncertainty, for mass and volume, so for both mass and volume, we quote one uncertainty, and it's 0.08% at the 95% confidence level. I have an animation here, hopefully it'll work for you, and this is just to show you the way in which the flow goes. So imagine the flow being this green ball. It's just a way to demonstrate it. So it's flowing around through the system. That's where the test meter would be installed, back through the pump and around again. So you can see it flowing around through the heat exchanger, down through the prover, through the reference system, and then flows up. That's the test section there. That's typically where we would install the device under test, be it a Coriolis, an ultrasonic, turbine, differential pressure device. And that's an image of it. So that was a nice SolidWorks. This is what it actually looks like. So you can see this is our existing James Young facility, and there's obviously other work going on at present in that facility. So there's like a water line that you can see here, our existing low pressure multi-phase flow facility. You can see the three-phase separator in the background. And then this facility here, this is the elevated pressure and temperature. And you can see that it's insulated and we have lagging as well. This is the test section. You can see a Coriolis meter installed just here. So we have other facilities at NAL. That's the elevated pressure and temperature liquid facility. We also have the national standards. So we are the national standards for oil flow and water flow. So all other measurements in the UK for oil and water flow are traceable back to NAL's national standards. So the oil flow facility uses a gravimetric primary reference. So you can see that there, it's the weigh tank. We also have positive displacement reference meters as our master meters, which is the secondary reference. For low viscosity fluids, that's where we install the test meters, apologies. For the low viscosity fluids, the primary gravimetric system has an uncertainty of 0.03% at K equals 2. The PD master meters have an uncertainty of 0.08% at K equals 2. And when we use high viscosity fluids, and that's termed anything greater than 30 centistoke, the uncertainty is 0.15% at K equals 2. And that's the same for both the gravimetric system and the PDs. However, for calibrating a Coriolis directly against our gravimetric system, the uncertainty is actually 0.05%. Now the difference in uncertainty, why is it so much greater? It's partly due to density. The effect of high viscosity fluids, the determination of the density is more challenging, has a larger uncertainty in our facility at present, and hence the overall uncertainty is slightly higher. We are doing work on that at present just now, hopefully to bring that value down further. So our facilities are UCAS accredited, or we have UCAS accreditation, and this is the front page of the sheet. It's actually recently been updated. We need to update that for a future presentation, although the values haven't changed, just the issue date has. So for the elevated pressure and temperature, you can see here it's the mineral oil facility, and the accreditation is 0.08% for that facility. So that's a bit about the facilities that I'm going to be presenting on. We obviously have other flow facilities at NAL, but I'm not showing data from those facilities, so I'm not going to go into a great deal of depth into those other facilities. In terms of customer data, we've calibrated a very large number of Coriolis meters. Pretty much all the main manufacturers that you can think of. We've done either customer work or we have completed R&D for the manufacturer. Variety of sizes and models. Models with and without Reynolds number corrections. So some Coriolis manufacturers have, or one in particular, has a patented Reynolds number correction. We've evaluated that device with and without the Reynolds number correction applied. We've calibrated across the laminar transition turbulent flow regime, calibrated across a range of pressures and temperatures, and we've also looked at the models of with and without their pressure corrections applied. So, Coriolis meters, typically known as being 0.1% devices for liquid, 0.05% for the elite devices. So the best meters might achieve 0.05, at least that's their specification. But by and large, most Coriolis meters aim for 0.1%. And I would also say that the majority do achieve that at the linear range at certain conditions with corrections applied. Also for gas, one of the real benefits of Coriolis meters compared to other devices is that the same Coriolis meter can be used for measuring liquid and gas. So not liquid and gas together, but liquid and then separately could be the exact same device could be installed in a gas line and used to measure gas. That's quite unusual. A lot of other devices that could maybe do that, such as a turbine, that wouldn't be the same. It'd be the same operating principle for the turbine meter, but it'd be a completely different device. A gas turbine meter is completely different from a liquid turbine meter, whereas with Coriolis meters, it's the same. But the mass specification for gas is 0.35%, so it's a higher specification, partly due to the lower mass of gas. So I'm now going to discuss with you some of the experiences we have with operating at elevated pressures with Coriolis meters. So I have an animation here of a Coriolis meter, obviously with the exaggerated shift, the Coriolis twist that you can see here. It's maybe not quite as prominent as that. What we have an inlet and outlet pick-off. The Coriolis mass, as mass flow goes by, it causes a shift in the Coriolis tubes from the inlet to the outlet. You get from the two pick-offs, you get a delta T. This delta T is proportional to the mass flow. Now, in terms of pressure correction, you have three options. So what we've got here, you can see that capital P that I have there. That's basically meant to be a pressure gauge located downstream as the flow is going from left to right. In terms of operating with a pressure correction, you have three options. You can have a static correction, a dynamic correction, or apply no correction. Now, what do we recommend? Well, I think the recommendation would be apply a dynamic correction. The static correction would also work, hence why we have a tick and a cross, but it's not ideal. If you imagine if you're operating in a facility or a process line, and you're operating at 20 bar, it might be 20 bar plus or minus 5 bar. So what correction do you apply? If it's only static, do you apply just purely the 20 bar correction? What about when it's operating at 15 bar gauge, or if it's operating at 23, 24, 25? The good thing about dynamic correction, it uses a pressure transmitter, feeds that into the flow computer, and applies an appropriate dynamic correction. Now, we also don't recommend applying no correction. We recommend applying a correction. We certainly don't recommend not applying a correction because pressure effects are significant, and I'm going to show you that in a second. One other point is if you're applying a dynamic correction, it should be traceable. So again, corrections are published in certain Coriolis manufacturers' data sheets, but these aren't all traceable. Certain regulators wouldn't be impressed if you were to use a non-traceable pressure correction. So try and get it from NEL or another flow facility that can operate at elevated conditions. So this is a low pressure calibration at NEL. So on the y-axis we've got percentage error. So that's a deviation between the flow meter and the reference, in this case the turbine meters. We have on the x-axis ref mass flow in tons per hour, and this is operating at 2 bar. Now you can see the performance isn't fantastic. It's fairly repeatable, but it's outside of specification for the first calibration. However, the good thing about Coriolis meters, you can adjust them digitally without needing to change anything mechanically. So you can change the mass factor, and we could adjust this meter, pulling up the performance so that it basically sat on the 0 line, apart from the lowest flow rates. So you could apply a constant correction factor that would just pull all the data up and make it well within 0.1% for the top 4 flow rates. So as I say here, the mass factor could be easily adjusted. I didn't adjust it in this case because we're looking at research on uncorrected devices. So we then followed up with some high pressure calibration points, which you're about to see. So we've got 10, 20 and 40 bar gauge. So I've still got the 2 bar data. We can now see the effects of operating at 10, 20 and 40 bar gauge with this this was a 6-inch flow meter. You can see that there's a definite pressure effect here. you can see that as pressure increases, so now at 40 bar, we're under reading by 1.75%. So that's fairly significant. It's massive, as I actually said here. It's a massive pressure effect. It's almost 20 times the specification when you're operating at just 40 bar gauge. 40 bar, relatively high pressure, but not extremely high pressure for liquid. And you're operating at minus, or you're under reading by 1.75%. So that's very significant. Now, if I show this data, this is still the same data, but now I'm just showing you the results presented with respect to reference pressure, so bar gauge on the x-axis as opposed to flow rate. You can see that it's linear. So you can see there's a linear effect, which is good news. If it's linear, it's easily correctable. So that's how we operate at NEL with the elevated pressure and temperature facility. Say a customer is operating at 20 bar. We might then perform a calibration at 20 bar, but we'd also do some additional points at 25 or 30 bar, and also say 10 or 15 bar gauge. That will give us a couple of pressures, and we can derive a linear pressure correction. We can then complete some additional points again at 20 bar to ensure that this pressure correction is robust. It's fully traceable, and we know the overall uncertainty of this correction. So that's a good thing about, although Coriolis meters appear to be affected by pressure, it's linear. Linear is good news because it's easily corrected. This is another Coriolis flow meter, so it's a different size, different manufacturer, different shape as well. And you can see, again, we've got a constant linear effect. Not quite as significant as, or as large as the previous device. You can see at 60 bar, it's close to about a 0.5% underread, but again, it's linear pressure effect. Linear is good news because it means it's easily corrected. So that's just some more data on another Coriolis meter. Just want to stress the point that pretty much all Coriolis meters are affected by pressure to some degree. It might be positive, it might be negative in terms of the effect. So it might cause an overread as well, as opposed to an underread. But there more than likely will be a pressure effect. It just depends on the significance of it. So, as I say here, there's pretty much always a pressure effect for Coriolis meters. Certain very small meters claim there's not a pressure effect. We've not done a great deal of work with the very small meters, and that's partly due to the limited flow range of this facility. We can operate from 0.5 to 100 litres a second. So below 0.5 litres a second for these very small bore meters, we've not done a great deal of research. Partly just due to the fact that we don't have a very small facility that can operate at elevated pressures. Now, what about density? So one of the main benefits of Coriolis meters, you can operate, you get mass flow, you can also get volume flow by combining with the density, but you also get density from the frequency output of the device. Density also appears to be affected by pressure, so this device in particular was significantly affected. Other models and manufacturers have seen, although they are affected by pressure for the density output, it's not quite as significant. For this presentation, I've used an example where the density pressure effect was fairly significant. But again, it's linear. And linear is always good news because it is correctable. So there does appear to be a density effect. A pressure effect for the density, sorry. So what do NEL recommend, or the Tuve National Engineering Laboratory, we often shorten it to NEL. We recommend that you try to calibrate as close to service conditions as possible, as feasible. It's not always going to be feasible if you're operating at, say, 200 degrees Celsius and 150 bar. There isn't a flow facility in the world that can operate or can calibrate devices at that condition, but hopefully you can try and get it close to. And the good thing about the pressure effect is you can work out what the pressure effect is by operating at a couple of pressures and seeing how linear it is, getting your linear pressure correction. And from the research we've completed, you can extrapolate the pressure effect to certain conditions. Maybe we wouldn't be overly confident extrapolating it to magnitude higher pressures. But if you're extrapolating maybe to an extra 10, 15, 20 bar, it should be sufficient. So we recommend the zero device at operating temperature and pressure. Calibrate the device at this condition as found. You can then perform an as-less calibration as required. Remember, that doesn't have an effect on the pressure effect. The pressure effect is basically the slope, so the gradient, and the adjusting the as found to the as left you can think of as being like the intercept, the c, basically in the y equals mx plus c. So you can then do the additional pressure compensation calibration at plus or minus 10 bar, for example, to derive this correction. And then you have this pressure correction that's fully traceable and meets regulations. So that's what we recommend, and that's pretty much what we do day in, day out with our elevated pressure and temperature flow facility as a commercial organisation. I like to think that's more helpful. I'd like to see something closer to that being detailed in the standards, just to provide guidance. How do you calibrate to operate your device at high pressure or elevated pressure and temperature? Now, I've went straight to viscosity. We do have some temperature data, but quite limited in how much time we have to present. Temperature does have a slight effect on Coriolis meters, although it's a magnitude less than pressure for the majority of manufacturers. You remember there's a lot of manufacturers. Can't speak for every device all in one because they do vary. There's over a dozen Coriolis manufacturers now. Some have done more research, some have better corrections. Remember, the reason temperature isn't as big an issue is because Coriolis meters have a temperature measurement on board. So they have an RTD that measures the tube temperature and it applies a correction. If this wasn't located within the Coriolis meter, although it always is, but if it wasn't, there would be a significant temperature effect. We've actually performed R&D at NAL with Coriolis meters and disabled the temperature measurement from the Coriolis RTD to ascertain the temperature effect, and it's significant. It's every bit as large as the pressure effect I showed you earlier. You can see 1 or 2% deviations, but because they measure the tube temperature and then correct for it, the effective temperature are much lower. The real effects you're seeing is if the tube temperature is different from the fluid temperature. So if your temperature is changing a lot and maybe the tube temperature doesn't have enough time to adjust, then you can have some effects. But if your temperature is stable, so even if you're operating at say 100 degrees Celsius, but it's constantly stable at 100 degrees Celsius and the tube temperature is close to that, it should be okay. It's really just if you have a varying temperature throughout the day. So imagine you're working in say the desert, for example, where it can be 40, 50 degrees during the day, then at night time it might drop down to be much cooler. You could potentially get deviations as the tubes are heating up and cooling down. So in terms of viscosity, with some other Coriolis research, this is some papers that are commercially available, so you can read them. You can see here they're on Science Direct. This is one talking about velocity profile effects on Coriolis mass flow meters. So they mention an important term here, the aspect ratio. The aspect ratio is, for Coriolis meters, it's the tube length over the tube radius. And this paper basically states that there's velocity profile effects in the laminar profile regime. That's below Reynolds number, typically 10,000, although it does vary with entry lengths. People define laminar flow below, say, 2,000, 2,300. A lot of papers show that you can get laminar effects depending on your entry lengths all the way up to 100,000 Reynolds number. It really just depends on how much installation you have upstream straight pipe work. What we find for this paper is smaller aspect ratios have larger velocity profile effects. So what that really means is smaller aspect ratios have larger deviations due to Reynolds number, so velocity profile / Reynolds number effects. That's what that paper stated, and that was back in 2006. There was another paper from Engers and Hauser back in 2010. They disagreed slightly with that previous paper, and they say that while it is velocity profile effects, one of the other dominating factors is viscous shear forces. So these viscous shear forces from elevated viscosity fluids actually reduce the Coriolis effect at low Reynolds number. So they cause a dampening of the Coriolis forces. So these viscous shear forces act in opposing direction to Coriolis. So the Coriolis force is twisting of the tube. They're saying high viscosity fluids dampen that out and cause an underread. And this is proportional with Reynolds number. Or this is in direct relation with Reynolds number. So the Coriolis force is dissipated in the secondary circulation. So the secondary circulation of the Coriolis force is dampened by these viscous shear forces. However, they state that above, say, 10,000 approximately Reynolds number, this effect becomes insignificant. So Enders and Hauser have a patented Reynolds number correction, easy for me to say, that they apply for Reynolds numbers below 10,000. So they do a calculation of the uncorrected Reynolds number. So they use uncorrected mass flow. They also know the tube dimensions. They know the fluid density from the frequency, and they can infer viscosity as well from the Coriolis flow meter outputs. They use all these uncorrected values to get an uncorrected Reynolds number. So it could be out by say 5, 10, 15%, but that gives them an approximation. They then apply a linear correction for Reynolds number, basically for the effect that these Reynolds numbers have on the mass flow output. I'll show you some data to show you what that roughly looks like. So this was some of the work we completed back in 2008 that I mentioned earlier when I first joined NEL. We had a low viscosity fluid, so that's kerosene, calibrated at 4 temperatures, 10, 20, 30 and 40 degrees Celsius. Because it's a low viscosity fluid, temperature doesn't really affect the viscosity too much, approximately 2 to 3 centistoke. Same as before, y-axis is the mass flow rate error, so that's the deviation between the device under test, the Coriolis meter, and our reference. In this case, it was our gravimetric system. On the x-axis, we have the reference flow rate in kilograms per second. You can see I've overlapped the Coriolis performance specification here. That's the blue lines. You can see that all the data is within specification. See, we're starting to see zero effects down the bottom there. You can see that for most of the points, it's starting to decrease. To the 10 degree points, it increases, but it looks like it decreases again at the lowest flow rate. But the vast majority of the results are linear, and they look very good. They're well within specification. Doesn't appear to be too much of a temperature effect here either. Maybe slightly. You can see the deviation between 10 and 30 degrees Celsius, but it's not overly significant. It's still within specification. We then operated with a higher viscosity fluid. So results were within specification. We now operated uncorrected with a high viscosity fluid. This time the trade name of this fluid is Primol. We operated again 10 to 40 degrees Celsius, and this gave us a Reynolds number range between 50 to 300 centistoke. And you can see that there's a definite Reynolds number of high viscosity effect here. However, we've also overlapped a curve for each temperature / viscosity. So you can see Primol has the data with a blue polynomial through it. We've got a lighter blue one for or teal for the 20 degrees Celsius. The yellow one we didn't put a curve fit through because there does appear to be a bit of separation, whether this is zero effects affecting the 30 degree data, but it wasn't quite as robust as the other temperatures. Now what we've done here in the next slide is we've looked at these results plotted against Reynolds number. So these results are outside specification, all apart from those two yellow points, just by chance, caused by zero effects. It actually made it within specification, but 99% of that data is out of spec. Now if we plot all the data, so that's both the kerosene and the Primol data, against Reynolds number, you can see that there's a definite Reynolds number effect, and it's linear. There's zero effects as well, so that's why you see some of those deviations, the yellow and the red points, and even the blue up at the top there. That's more than likely zero effects. So Coriolis meters strongly affected by the zero. I'm not going to go into too much detail about what the zero means. I might do that in a future webinar, maybe purely on Coriolis meters. We'll discuss the operating principle and the effects of zero. But you can see there's definitely a linear Reynolds number effect. So one of the main manufacturers, Enders and Hauser, now have a patented Reynolds number correction, and it takes into account these Reynolds number effects. So compensation is possible versus Reynolds number. There is patented Reynolds number correction, or you could apply something similar in your flow computer, basically with a calibration curve. You just need to make sure you don't fall foul of the patent. So what do we recommend? So our recommendation would be calibrate with respect to Reynolds number if you're operating with relatively high viscosity fluids. So if you're coming to a facility such as NEL, we'll work out what your Reynolds number range is. So if you let us know your conditions, we can work out what the Reynolds number range is. We will then match this Reynolds number range with one of our high viscosity fluid, maybe at 2 or more temperatures. So we might operate with a couple of viscosities. That gets us a wide Reynolds number range. We then zero the device at operating temperature and pressure. We calibrate the device at the Reynolds number as found. We decide if the Reynolds number effect is significant. Now I must stress this. I said before that for for pressure, all meters were affected. What we're finding for Reynolds number, not all meters are affected. That aspect ratio appears to be significant. It's definitely true that not all Coriolis flow meters have a significant Reynolds number effect. It appears to come back to, as I say, that aspect ratio. Certain devices are affected, others aren't. So we'll decide if the effect is significant, and then we can perform an as-left calibration if required. So again, remember, it's going to be that linear effect, but you can adjust. You can pull the results up or down as well. So you're still going to have the linear effect, but you're going to basically be changing the offset when you do that as found as left calibration. Some more experience. So the EPAT facility that I mentioned here, this is true of all our facilities actually. We have a program known as MeterView, which is extremely helpful in the current environment just now. So COVID-19 means there's obviously travel restrictions. People can't come to NAL's lab to witness calibrations, but we invested in some software several years ago. We've been operating with this MeterView software for several years now, very successfully. It means that customers all over the world, so we often get customers from the Middle East, from Southeast Asia, from America, etc. They all remote in and they can witness their calibration remotely and actually speak with the test engineer. So that's obviously Scotland there, and then that's our flow laboratory. MeterView allows end users to actually remotely witness their calibration. They can ask for repeat points, they can change the conditions. If a point doesn't look correct, if there's maybe an issue with it, or they want to ascertain the repeatability, they can be in contact with the test engineer and ask for them to repeat a point. So it all works very well. So I highly recommend that. So that's just a bit about what we're doing at NAL, some of the main things we have this MeterView software. In terms of conclusions, the Coriolis water calibration doesn't fully replicate service conditions. Now, when Coriolis meters are produced in the manufacturer's facility, they perform a water calibration to get the flow calibration factor for that device. So when you get a meter from the manufacturer, it will often be shipped with a calibration certificate from water. Now this is great to have, but you can't just rely on that calibration. If you're going to be operating in elevated conditions, you should try and calibrate close to service conditions. Next point is that the vendor published pressure corrections are not traceable. So not all manufacturers publish a pressure correction, and even the ones that do, not all the pressure corrections are traceable. So you can't just rely on the manufacturer data sheet. Temperature affects a magnitude less than pressure, and that's not due to the physics, that's more due to the fact that it's compensated for directly. Coriolis meters have a RTD to measure the temperature and correct for it. They do not ship with a pressure probe to correct for pressure. So you have to either apply a constant correction, apply no correction, which a lot of people are unwittingly doing, or apply a dynamic correction with a pressure transmitter into the flow computer or into the software of the Coriolis meter. If you're operating at low Reynolds number, you should characterise it. So if you're operating high viscosity, characterise it against Reynolds number where possible, or at least ascertain if the Reynolds number effect is significant. This is crucial, this point here. The performance of Coriolis meters from one vendor to another are not necessarily similar. There are many other variables such as aspect ratio, R&D, even just the history of them producing it, working out if there is a pressure effect, temperature effect, correcting for it, the design, their frequency at which they oscillate. There's a lot of different things that affect Coriolis meters, so it's not true to say that they're all the same. They differ from vendor to vendor. So I'd like to thank you for listening. We've got some questions that have been coming in, which is great. I hope you've enjoyed today's presentation. As Marietta said at the start, limited to time, so I can't answer all your questions. But if you want to email me or email Marietta or email NAL, I'll be sure to reply back. Hopefully be able to answer any of the questions you might have that we can't cover today. I'm just going to have a look through some of the questions that have came through. So if you just give me a minute. So one of the first questions I got here, actually it's not so much about Coriolis meters, so it says that, so I'm going to read the question out. It says, are ultrasonic flow meters affected by temperature and pressure in the same way as Coriolis flow meters? Now that's a good question. So Coriolis mean one of the main types of flow meters that people currently use in industry just now. At least 90% of the meters that we see in air are Coriolis, but we do see a lot of ultrasonic meters. Now they are affected by temperature and pressure, but maybe not in the same magnitude as Coriolis meters. Most ultrasonic meters, so they're full bore devices, typically for liquids anyway. They're full bore devices, and all that really seems the temperature and pressure effect seems to affect is the geometry of the device, and the standard actually details what happens with this geometry, the changes with respect to temperature and pressure. So ultrasonic meters do appear to be slightly affected by temperature and pressure, but from the research that we've completed, it's not extremely significant. I'd like to do more because same with Coriolis meters, there's a lot of different manufacturers, different meter sizes. We've only done limited research, but from the limited research, I would say that the effect isn't significant at present. It doesn't appear to be significant at present, but maybe more research is required. That's an interesting question. I think I've got time for one more, so I'll just have a look here. And it's what it says here is actually, sorry, this is another one that's quite good. It says, how often should you calibrate a Coriolis meter with respect to pressure? Now that's again a great question, because most recalibration intervals for flow meters, irrespective of the technology, is 1 year. Depending on your agreement or your regulations, most people try to recalibrate their flow meters on a yearly basis. Now, should you perform the pressure correction or calibration every year? What we would recommend, so we are now seeing this because we've been operational for 4 or 5 years now, people are now coming back to NEL, and we're finding that the pressure effect doesn't change, or it hasn't changed so far. I can't say with certainty that it won't, because depending on your operational conditions, maybe if you're operating with varying pressures constantly, maybe this will have an effect on the meter, and the pressure effect might change, might deteriorate the device. The pressure effect might become more significant over time. But from what we're seeing just now, it doesn't appear to be changing significantly, but I think it's still worth checking. So what we'd recommend for your recalibration after doing your first is just come back to NEL, say you're operating at 20 bar, you perform your calibration at 20 bar, and we can compare that with your previous calibration. That will allow us to ascertain whether there has been any significant shift. If there has been a significant shift, we can perform very quickly, because to change pressure in our flow facility is extremely quick, because oil is fairly incompressible, has a low compressibility. We can change pressure very quickly, and we can do a quick check to see if the pressure correction has changed. By and large, of all the checks we've done so far, we're finding that it's not changing, certainly within the uncertainty of the flow facility and the specification of the flow meter. So it's a good question. Our recommendation is stick with your recalibration interval, and you can ascertain whether you have to perform this additional pressure compensation again. What we're seeing so far is no, you don't have to, but you're best to recalibrate close to service conditions. So I think that's all the time. It's at 5:02 now, so I'm going to pass you back to Marietta. Thanks for joining me today.